Hello everybody, my name is Hoang Hai Anh and today I would like to present about topic related to lithium battery field. And my topic have titled High voltage stable solid-state lithium batteries based on the nanoconductor embedded flexible high-base solid electrolytes with hyper-ion conductivity and thermomechanical and adhesive stability. And first let's start with some basic information about lithium batteries. As we know, in the digital era, the emerging diverse and innovative technologies have generated burdening demand on energies under the depletion of natural resources, and variety of new energy storage and generator systems has been explored to respond to this requirement. Lithium-ion batteries is one of the potential devices because of its overwhelming advantage, including high energy densities, long cycling time, small cell recharge, and small memory effects. So, as we know, since the drawback of the liquid electrolyte utilized in the conventional lithium batteries are obviously exposed, much more attention has been paid to the development of solid-state lithium battery systems with higher safety and electrochemical stability. And this solid-state lithium battery system, however, face several critical barriers towards the commercialization because of some problems associated with the solid electrolyte materials. And as known, there are generally two types of solid electrolyte, which are inorganic ceramic electrolyte and solid polymer electrolytes. And generally, the inorganic ceramic electrolyte exhibits the inverse thermal and mechanical permanence and excellent lithium conductivities, but poor interfacial contact with the electrode. On the other hand, the solid polymer electrolyte displays a high flexibility and good chemical and interfacial stabilities, but relatively low lithium conductivity and lithium transfer number. And consequently, the development of a new type of solid electrolyte with balancing the superiority of inorganic ceramic electrolytes and solid polymer electrolytes is a task challenge. Another problem we need to care to maximize the capacity of lithium batteries is active materials. And as noted on, the lithium cobalt oxide has been used as one of the most popular active materials for the cathode. And even though the lithium cobalt oxide has a high theoretical capacity of 274 mAh per gram, its practical values has just been around 140 mAh per gram when it was applied at the upper cutoff voltage of 4.2 volts. So to maximize the electrochemical performance of the lithium batteries, the upper operating voltage should be increased to 4.5 volts, which is generally known as the theoretical working potential, and with high voltage working condition. However, induce some serious problems such as the oxidation and decomposition of electrolyte and active materials, which ultimately damage the physical-chemical stability of the batteries. And therefore, to realize a high voltage stable lithium batteries, the aforementioned problem of the solid state and high voltage working condition should be thoroughly resolved. So in here, we shall set the concept of the association of strong attraction and mechanical strength of the PVA and wide electrochemical window and excellent thermal stability of pyridine-based ionic liquids, and their combination can express the superior characteristic of a solid polymer electrolyte and wider application. However, as the synergetic effect of the PVA and the pyridine-based ionic liquids blend is mitigated by the immiscibility between them, and their compatibility is purposely improved by graphing the PVA with the PCA unit, and the 3D matrix of the well-constructed PVA coupled PCA and ionic system not only enable the feasible interaction with the lithium ion by the abundant and electronegative groups, but also provide the effective lithium transport in the presence of the ionic liquid. On the other hand, is ATPJ nanoconductor was introduced to the PVA graphite PCR liquid-based electrolyte to further increase the lithium transfer number and reinforce the integrity of whole battery system. As this structure mimics the sequence of functional group of PVA graphite PCA, ATPCA nanofiller was quite compatible with the PVA graphite PCR liquids and thus possibly supply additional 2D free-wave lithium transfer number as shown. And the nanocontainer of the ATPCA creates the selective transfers towards the lithium ion to enhance the lithium transfer number because its small dimension and small, and also restrict the transfer to the bulky ion liquid cluster composed of the PIR pyrrolithium cation and TFSI anions, and to suppress the oxidation and decomposition of active material. At high voltage, the lithium carbon oxide particles are coated with the aluminum nanolayer by the solder method, and this protection layer hinders the formation of high-valence carbon anion and thus suppress the fading and decomposition of the lithium carbon oxide at high potential. And based on this strategy, the high-voltage solid-state lithium batteries are systematically fabricated and combining the ATPCA embedded PVA graphite PCR ionic liquid electrolytes and surface-protected lithium carbon oxide cathode material. The PVA graphite PCA polymer material was simply synthesized by esterification reactions, and the ATPCA nanoparticles were synthesized by co-precipitation methods as shown in the slide, and due to the time limitation, the specific result of this topic was not contained in this presentation. Thanks for your listening.